Oh, hi everyone. I do ever so appreciate you showing up and learning some math things. Yeah, you're all on video now. Yeah, well, not on the video, but your side chats are. Okay. So, Connor, while you're up there, do you mind erasing the board? Just up there. This part. Like 100 some? Why, you want to be 101? I'm not in this for the cash, you know this, right? Okay. So, today our goal, this is what we want to, this is a new idea that we want to understand. We want to understand the a value in a quadratic function, use those properties to graph a function, and understand stretches and reflections. So stretches and reflections are like our new idea today, that we're actually deforming our functions and moving them around like they're elastic bands or something like that. So yesterday we looked at y equals x squared. It's the most basic parabola. If I want to go like y is equal to -3 squared to evaluate this one, I very carefully substitute into brackets and work out that that's 9, that's 4, that's 1, that's 0. Oh my goodness, it comes around and goes back up again. So that we have this beautiful function here, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is indeed there. Okay, boop. And then this one is 4, so it's there, and there, and there, and oh, that one there. And we see the vertex there, right? It's 0, 0. Also happens to be the roots, happens to be the minimum value of this parabola. Oh, it's nice and smooth down there and comes up. Spikes those points just beautifully, just misses them so beautifully. Okay, anyway, so we can think about this quadratic and think about its like vertex and its direction of opening. It opens upwards, right? It opens this way. It goes like that. It looks like someone's celebrating a win. The vertex is at 0, 0. Okay, cool, that's good to know. And the step pattern. When we talk about step pattern, this is not something that I would evaluate, but it is something you can use to very quickly visualize your parabolas. If I go over 1, I go up 1, and then I go over 1 and up 3, and then I go over 1 and up 5 to that point there. Okay, and this pattern of the odd integers there, 1, 3, 5, absolutely continues off to infinity. So this thing continues growing by 7, 9, 11, 13. You've been counting by those for a long time, so that's pretty useful. So that's what we would call the step pattern, is 1, 3, 5. It's when I leave the vertex traveling right, how much do I increase by? When I leave the vertex traveling right, how much do I increase by each step? Now today we're going to make changes to this equation and see how it changes the resulting parabola. Let's go. What's going to happen here when we've got g of x is equal to 2f of x? Okay, we're making a new function. F of x was x squared. If I do 2f of x, well, that would be equal to 2x squared. Okay? So I can simplify g of x as equal to 2x squared here. I have multiplied a function out there, and it's given me a new function with an a value of 2. So change that a value for us. All right, so then we get, well, when I do 2 times minus 3 and I square it, I get 18. I do my work very carefully. I've got 18, 8, 2, 0 still, 2, 8, and 18. So then I graph them. There's 0, 0. There's 1, 2. Here is 2, 8. So that one. And then we're mirrored over there and there. So I transfer my points onto the graph, and it looks like this. It's much kind of like sharper turnaround there. Oh, but Mr. Jennings is getting better at graphing these quadratics. Oh, there we go. So there's what this one looks like. And then if we analyze its step pattern, we would find we go over 1, up 2, over 1, up, oh my goodness, 6. And so here, and then I wonder what would happen over here if we went over 1. Maybe I could do this here. Oh, it's up 10. And here it is there, up 6 and up 2. So the step pattern is also the first differences as you leave the vertex, going right, going bigger values of x. Okay? And so then, the way that I want, that if you want to use step pattern for graphing quadratics, the way to make this useful is, first of all, we notice the vertex is still at 0, 0. The direction of opening is still up, but the step pattern is now 2, 6, 10, dot, dot, dot. So that's an interesting pattern of even integers growing by 4 each time. It's kind of awkward. We haven't been counting by those for a long, long time. But here's how you can do it. You take this 1, 3, 5 from before. Okay, that was the step pattern for our basic function. Y equals x squared. Okay, we're going to take that step pattern and multiply it by this number here, 2. By this number here, 2. Okay? Our a value. So we just multiply that step pattern by 2, and it gives us 2, 6, 10. Same idea. So that makes the a value very useful for graphing quadratics. Because we know this 1, 3, 5 of the parent function, or this x squared business, then we have, then we can very quickly just find the new step pattern by looking at the new a value. With that one that was like 4.9 meters per second, I could have used that idea, but it would have been a little bit of a rigmarole. Okay, here, h of x is equal to 3f of x. Okay, well I remember f of x was just x squared, so that's this function 3x squared. Okay, so h of x is equal to 3x squared here. And then we would get, well, if I put in minus 3, so h at minus 3 would be equal to 3 times minus 3 squared. Oh, that happens to be positive 27. And we would be 27 here, 12, 3, 0, 3, 12, 27. Okay? This gives us a parabola that's way off of our graph. It goes like this. And the next one is just up there. Actually, it's not that sharp. It's just up there. That's the point minus 212 that we would go through. And here, let's make a prediction about our step pattern before we test it. We know that the typical step pattern was 1, 3, 5. But here we are multiplying by 3. So our new step pattern will be 3, 9, 15. So let's check. Our first step is over 1, up 3. And the next one is over 1, up 9. And that would get us to the point 212. Right there. So our trick worked. Still the same. So that way you can bypass making tables of values if you want, if you know how the original x squared function has been deformed by that multiplication. Okay? So the vertex, I mean, it didn't change. It's been 0, 0 all day, and the direction of opening is still up. With this one here, j of x is 0.5 f of x. Okay, 0.5 times x squared. So we have j of x is equal to 0.5 x squared. Okay. Then if I evaluate it here, I'm going to get j at minus 2 is equal to 0.5 times minus 2 squared. Minus 2 squared is 4, so I have 0.5 times 4. 0.5 of 4 is 2, so that's now 2. Okay. This one over here, also 2. It's symmetrical. Let's check this one here, 3. let's do this one too, and these ones. This one's 0. J at 1 is equal to 0.5 times 1 squared. That's just 0.5. So that's 0.5. And then 3. J at 3 is equal to 0.5 multiplied by 3 squared. 3 squared is 9, so this is 0.5 times 9 is 4.5. 4.5. So let's graph this one, see what it looks like. We have 0, 0 there. We have 1, 1/2, halfway up to 0. We have 2, 2. Yep.
Why is square, like J3 equals 0.5 times 3 to 2? Like why can we do that?
Oh, because we have j of x is equal to 1/2 of f of x. J is equal to 0.5 f of x. It's just the example that we're looking at. So now I'm showing you, this is what you would do if it was a decimal. Okay. And then it creates this new function, 0.5x squared. That is j of x, 0.5x squared. Taylor? Sorry? No, it's squared because that's the function, f of x. F of x is this function up here that we looked at. Oh my goodness, I didn't call it f of x here. F of x. So, let's change it. It's a long story. I'm going to put a mark up there in a second. So that's why it's x squared. Where? It's my fault. I have an error to mark. Chase, do you want to mark my error? Just finish the tallies. So here's what happened. I took this handout from another teacher, and I was like, I like their handout, but I'm going to improve it. And when I did, I didn't realize that they had called this just x and y up here. I thought they started with f of x. Because they moved on to g of x, h of x, and blah, blah, blah down here. And I thought, well, we would take this morning when we did like 2f of x, 3f of x and stuff, we've already kind of looked at that idea of just I multiply the parent function. So I thought we would continue that for the lesson. But we didn't have it here. So that's why that was my error. I should have fixed that there so that f of x is x squared for the whole handout. So it's my fault, Ava. So I appreciate people pointing out their confusion. Thank you. J of x, just take my word for it if you're still confused, is this function 0.5 x squared. Okay? It's half of x squared, half of f of x. Okay? When we put in our points, we're going to get these points coming out there, like that, and then symmetrical around here, like this. And if these are ever like bugging you or you want to see them more clearly, you can always throw them into Desmos. F of x is equal to x squared. So we define that one. We could put in our points quickly like this. So there's our various points that we've looked at here. I just want to see number 3 there. So there's our points. And then if I wanted to see j of x is equal to 0.5 f of x, there it is there. Let's make it a table as well and see this one 3. So now check that one out. There's our points 1, 0.5, 2, 2, and 3, 4.5. So we can do that pretty quick in Desmos. Yes, I encourage you to do your textbook homework alongside Desmos because Desmos is really going to support your learning. There will be times to demonstrate the learning that you've done with Desmos. Desmos won't be available on the quiz though, or sorry, on the test. So it's a practice tool and a very powerful practice tool that you can use. All right. So let's take a look here. If we look at our step pattern now, we have moving over and up by 0.5, moving over and up by 1, moving over and up by 2.5. Okay? So there's our values for our step pattern. It ended up being 0.5, 1.5, and 2.5. Notice that if I do 0.5 times 135, that base step pattern, I get 0.5, 1.5, 2.5 there. So I get that. There's my step pattern. Anything else that I can help clarify? No? Okay, cool. All right, so it still opens upwards. Its vertex is still 0, 0. But the step pattern is now squished, and it's squished by a half. Okay. So now if we look at, say, minus 2x squared, so now we have this new function, f of x is minus 2x squared. If I put in minus 2 times 3, but it's negative, squared, in this case, do I get positive 18 or negative 18? This time I get negative. Because negative 3 squared is positive 9, but I'm still multiplying that by negative 2. So that's going to give me negative 18. Our other values here are negative 8, negative 2, 0, negative 2, negative 8, and negative 18. Okay, we can test one of these. Let's test this one just as a thing to do. F at 2 is equal to negative 2 multiplied by 2 squared. 2 squared happens to be 4 times negative 2. 4 times negative 2 is indeed negative 8. So this one graphs over here. Boop, boop, boop. And over here down at minus 8, 3, 4, 5, 6, 7, 8. There. And there. Okay, so this function, oh, it's flipped. So that one's going to look like this. Yeah?
Why are you putting the square on negative 3, like for the first?
Yeah?
Why are you putting on the negative 3 when the f of x is equal to the negative 2x squared?
So here's so f of x is this function negative 2x squared, right? I'm not sure why I wrote brackets there, but they don't change anything. I could keep the brackets. So now if I put in f at negative 3, I'm going to keep this negative 2. I'm going to have negative 3 in brackets, because I always substitute into brackets, and then I keep that squared. Right? Now I square the bracket, which is negative 3 times negative 3, positive 9. Right? So negative 2 times positive 9, and that gives us 18, but negative. So that's how that one do. Okay. So now we notice, hey, our direction of opening is now downwards. Our vertex is still 0, 0. So none of these stretches, none of these numbers that we're multiplying the function by have changed the position of the vertex. But now we've seen they can change the direction of opening. What is it about this number minus 2 that made it open downwards? Is it the 2 or is it the negative? It's the negative. When I multiply a function by a negative, it reflected the function in the x-axis. All the positive things became negative. All the negative things would become positive, and it would reflect around the x-axis like the x-axis was a mirror. Okay? And then, otherwise, the 2 stretched it all by factor 2. And we can see those stretches there. Our new step pattern idea still works. Here is go down 2, go down 6, and then the next one would be go down 10. Okay? Those come from 1, 3, 5 being multiplied by minus 2. There's minus 2, minus 6, minus 10. So, all of those equations were of this form. F of x is equal to ax squared. They're all similar to y equals x squared, but when we multiply the whole function by a number in front, it stretches or compresses the number. Sorry, compresses the function. And when the number's a negative, it reflects the function in the x-axis. Everything positive becomes negative, everything negative becomes positive in terms of the y values, the outputs of the function. Okay? That's the main takeaway there. So that way you could sketch the graphs of f of x and g of x here, these new functions given, without making a table of values, just by stretching those functions. Just practice making some quick sketches there. One question type I want to review before I release you. This here, we got textbook work to do. I don't want people to spend 2 hours over the weekend doing this stuff, but 20 minutes to 40 minutes is a reasonable amount of time to spend over the weekend, I believe. If you can, find it, that's great. Here's the schedule for the rest of the week. Monday, final lesson. Tuesday, Wednesday, catch up and review days. Thursday, we'll do an evaluation. Friday, you'll get a chance to respond to the feedback you get on the evaluation and take next steps in your learning, which is also worth marks. Okay? Let's take a look at question number 2. If I know that the point 412 is on the graph of y equals ax squared, how could I then find the value of a? How would you solve a problem like this? Yeah. If you're confused about how to do this one, come to my workshop on solving equations at lunch in 224. But here's what we would do. You sub it in. That's good. For y and x. Y equals 12. X equals 4. So we have 12 equals a times 4 squared. I just substitute into that equation. 12 equals a times 16. Divide both sides by 16. A equals 3 on 4, which is the simpler way of saying 12 on 16. That's the value of A, because this cancels. That's how that one do. Jude?
For the workshop on solving functions, is that like today?
No, it's going to be today. Yeah, just today. If you can't make it today for some reason and you want to do it another time, I'm happy to sit down with you and solve some equations. But if people want to come today, I think I have students that are coming. I haven't seen a lot of the math club students yet this week because it's been snow days and stuff. But there should be students there to help us with solving equations today in 224 at lunch. Bye for now, everyone.